Hi, welcome to the demonstration corner. My name's Kelsey. I'm an application specialist here at Thermtest, and today we're going to be going over the MP-1 with TPS Finite method. Available on our advanced measurement platform, the MP-1, the Finite method is a new addition to the standard TPS method. To give a little background, the TPS method available on the MP-1 follows ISO 22007-2 and 22007-7 for testing thermal conductivity, thermal diffusivity, and volumetric specific heat of solids, pastes, and powders. The Finite method extends the TPS method to measure isotropic and anisotropic materials, which are short, small, cylindrical samples with well-defined thickness, less than 8 millimeters. This allows you to test samples that cannot be tested with other traditional methods like TPS bulk, 3D bulk, or 3D SLAD. This method also allows you to measure accurate thermal conductivity, thermal diffusivity, and specific heat for small cylinder-type samples up to 500 watts per Kelvin, which can be difficult to measure with the standard 3D semi-finite method due to small penetration depth, often requiring the input of specific heat or larger sample sizes. My colleague David Landry, our research manager, will now give more details on the method and the theory behind it. Then we will go through how to set up a sample with the MP-1.
Hello everyone, I am David Landry, the Thermophysics Research Manager at Thermtest, and I will be giving a brief overview of the Finite method, a sort of advanced test configuration for the transient plane source. The transient plane source method, which is covered by ISO 22007-2, is for testing semi-infinite samples with a disk source that acts as both the heater and the sensor. So you have a thin nickel element as your heater, and that heats up two samples, one on either side of the heater, and the change in resistance of it gives a transient temperature rise. This is used for the simultaneous determination of thermal conductivity and thermal diffusivity of the samples tested, and the ratio of those two properties gives also the volumetric specific heat. This method is for testing semi-infinite samples, so in the critical dimensions, the heat must be able to travel effectively an infinite distance, or just the sample has to be large enough that the heat doesn't interact with the boundaries. For bulk, pictured on the top left, this is in every direction. The heat can't interact with any boundary. And for slab, which are samples of a specified height that is generally a little smaller than the radius of the sensor, it is the radial direction of the sample that has to be effectively infinite. So you need very wide samples. This gives two clear limitations, both coming from heat interacting with the boundary, and that is high conductivity samples, where heat will penetrate through a large distance very rapidly, and small samples, where there just isn't a lot of distance for heat to penetrate through before interacting with the boundary. The usual way of dealing with these limitations, particularly for the high conductivity limitation, is to try entering the volumetric specific heat of the sample measured through some other means and adjusting the calculation window to try to get good results. This changes the method from measuring two thermal properties and calculating a third one into a method that only measures a single thermal property, and the rest is calculated or already known. This is obviously much worse. To deal with these limitations, we developed the Finite method for testing cylindrical samples of known height and radius. And this method accounts for both the axial and the radial boundaries. By doing this, it gives flexibility in a couple of areas that can be considered as linked to available probing depth for the heat, which are sample size, test duration, sensor selection, and thermal conductivity range. How is this accomplished? In the mathematical formulation, as always, you start with the heat equation. And so on the left, you have the portion relating to heat conduction in a solid, with the thermal properties of that solid, the radial and axial thermal conductivities, as well as the volumetric specific heat. And on the right, you have the heat source term for the system, which is just a constant power disk of a specified radius at the center of the system. And then you describe the boundary conditions. This is insulation at both the radial and axial edge. That is, the derivative with temperature with respect to that direction is 0. Solving the system with the usual mathematical methods gives formulation for the temperature, which depends on time, power, the geometric properties of the system like the height and the sensor radius and the sample radius, as well as the thermal properties of the system, which are again the volumetric specific heat and the directional thermal conductivities or thermal diffusivities, depending on how you want to write it. Let's put theory into practice with an example that covers both of the limitations of the usual method, and that is testing 2 small cylinders of copper with a 1-second test duration. Both of the copper pieces are 1 millimeter tall and 12.5 millimeters in radius, or 1 inch in diameter. The thermal conductivity of copper is expected to be around 400 watts per meter Kelvin, which is very high, and the thermal diffusivity is expected to be around 116 millimeters squared per second. For a 1-second test, this gives an expected penetration from any point in the source of 30 millimeters. From the center of your sample, if there's only 13 millimeters of depth available, you can intuitively understand that heat will reach those boundaries very quickly. And this is reflected in the results when you try to use the different calculation methods described by the ISO on this system. If you try applying bulk or slab calculations, either with or without fixed volumetric heat capacity, the results you get are plainly nonsense, 90 to 100% off in terms of every thermal property. This is also seen in the residuals, which are supposed to be normally distributed, but for both bulk and slab exhibit a clear pattern which shows that not all the thermal behavior in the measurement is getting accounted for in the mathematical formulation. However, with the finite method, we can see that the thermal properties as measured are all very close to what they should be. The thermal conductivity, diffusivity, and volumetric specific heat are all within 1 to 2% of their expected values. Further, the residuals are normally distributed, showing that all the thermal behavior that is experienced in the transient is being accounted for in the mathematical formulation. This is an excellent measurement on a difficult sample and shows the benefits of the finite method. Thank you for listening, and I'll pass things back over to Kelsey.
So now we're going to go through a quick setup of the TPS finite method. So we have small cylindrical samples of brass that are 5 millimeters tall. So to set this up, we're first going to connect our TPS sensor to our stand. We're going to place insulation on either side of the sample to enforce the boundary condition. Then we're going to place another piece of brass on top and another piece of insulation for symmetric setup. So now we can clamp this all together to ensure good contact with the sample and the sensor. And now we can move over to the software and begin a measurement. So now in the software, we can go down to our schedules page, and under method, we can select 3D disk source and finite sample. So then we can enter our operator ID and select the location to save our test result. And on the sample page, we can enter all the information relevant to the sample that we're testing. So today we're measuring brass that's 5 millimeters tall and has a radius of 10.5 millimeters. The sensor we're using to test this is a 3317-1 sensor, so we can check the resistance of that sensor. Okay, perfect. So now we can set up our schedule. So we are going to run a series of 5 tests with a 10-minute delay between each test, with a test time of 1 second and a power of 3,000 milliwatts. So then we can just hit start, and our measurements will begin automatically. So we've already run some measurements on this sample, so we can take a quick look at that in our analysis software. So here we have 3 tests run on the same brass samples with the 3D finite sample method with 1 second and 3,000 milliwatts. So if we select all 3 test results, and we review our experiment results, we can see our conductivity, our thermal diffusivity, effusivity, and volumetric specific heat results. So that's all there is for the analysis. In review, the finite method was developed to accommodate small disc-shaped samples that cannot be tested with other traditional modules like 3D bulk or 3D slab. Along with our other patented advancements, we continue to strive for the intelligent MP-1 to be at the apex of thermophysical instrumentation. If you have any questions or want to see your own demo, please contact us at info@thermtest.com or with the information in the description. Thank you.